In this lecture, we're going to look a little bit more at torque and hopefully move on to talk about moment of inertia a little bit. First thing that I want to mention is, why is this torque idea useful? Because I've taught you now that it's force times the lever arm, so basically the distance from the point of rotation to the point of application of the force. What does that do for us? And if you think about lots of different tools that you have, for instance, if this is a door, let's just start there. So they place the doorknob pretty far from the axis of rotation, and the reason why they do this is because it's a lot easier for you to twist the door if you can apply your force at a large distance from the axis of rotation. So if they put the door handle over here instead, right near the actual hinges, you would push on this and you would kind of get the door open, but it would be really, really hard. And you might have noticed this with the push bar doors, where if you don't apply the force towards the end of the door away from the hinges, then it's a lot harder. If you push towards the middle, it's not so easy to open it up. Another way, still talking about doors, is if you have door stops, you wedge the door stop in close to the edge of the door. If you put it close to the hinges, it doesn't work. And I remember fairly early on in my career here, there was another teacher, who was having difficulty keeping their door open, but they were trying to put the door stop in the middle of the door. That means that you're only taking advantage of this relatively small lever arm for the force that you're applying with the door stop. If you move the door stop out, you can get a bigger force applied. Some other examples of how you use lever arms: a wrench. So if you have a wrench and you try to twist a bolt with it, by applying the same force that you could maybe with just your hands, you're able to get it to twist because you're applying that force from a greater distance away. Back when I was student teaching, we were building a trebuchet, which is basically, well, like a gravity-powered catapult. And it was really big, and we were using really big pieces of wood and really big pieces of metal. And there was one bolt that we couldn't get to go through because it was grinding up against the metal of one of the plates that we were using to connect pieces together. And so what we did was we took the wrench, and then we took like a 3-foot long piece of PVC pipe, and we just rounded around in circles. And I mentioned this before, I think, in reference to work, but it turns out that it's actually very similar and related with the idea of torque, because what we did was we increased the lever arm so that we were able to apply a lesser force than we would have otherwise been able to. Other examples of this include screwdrivers. If you ever take a nail, or a screw rather, and you try to twist it with your fingers, it's hard. But you get a screwdriver, and you're increasing your radius by maybe a factor of 2 or 3, and that's enough to make it so that you can actually twist it. A sink. If you take the handle off of a sink, one of the sinks that have the handles that you twist, if you take one of those off, it's very difficult to actually get the water to turn on and off. But with this handle that you can grip and twist, it becomes much easier. And this is also true of, like volume dials, that sort of thing. If you take the volume dial cap off of something, then there's just a little tiny nub in the middle, and if you try to twist that, it can be quite difficult. So that's kind of the purpose of torque, and the idea of lever arms is that the larger the lever arm, the smaller the force that you need to cause something to twist. But now let's talk about direction with this, because it is a vector. So if I have some sort of a wheel or a disc, and I apply a force at some distance away from the axis of rotation, we'll assume that that's in the middle right here. That's, by the way, the middle. So we get these forces in radius, and if you think about what's happening here, you can hopefully realize that by applying the force to the right at the top of the wheel, we would cause the wheel to twist clockwise. So our torque would be clockwise, but we don't define it as clockwise, we define it as, in this case, this would be into the screen. So for us right now, clockwise is into the screen, and you might be wondering, how did I get that to happen? So what I would do is I would take my hand, and I would basically wrap my fingers around in the direction that the wheel would be going. So I start off with my hand maybe at the top of this, and then I just curl my hand around so that it's curling around the wheel in the direction that the wheel is going, so basically moving clockwise. And my thumb sticks off to the side and actually into the screen. So you can try this. We'll do more hopefully when I'm back. We'll do more with this and talk about this thing that I'm doing with my, by the way, I mentioned I think that it's the right hand. This thing that you're doing with your right hand, it's called the right hand rule. And there's actually several right hand rules. We'll get into that a little bit later. But for now, just recognize that this R and F gives rise to a torque that's into the page. You might be wondering why into the page. So let's get into that. Let's say that I've got another force. So this is the same R. And I've got another force that's directed like this. So in the first case, our force was off to the right. Now I've got another force that's down. And if you think about what this force at this position is going to do, it's also going to cause it to go clockwise. So basically it's going to apply a torque that's also into the page, or into the screen. So this is where it gets tricky. I have a force that's to the right causing the same effect as a force that's down. And it doesn't take much imagination to realize that I could do the same thing right over here like this, where now I have a force that's up and it's causing the same effect as a force that's down. So I can't use up and down because I can get the same twisting effect by applying an up force as I can a down force. I can't use left to right because the same thing is true. So I can't use left or right, I can't use up or down. What's left? And so if we only have 3 spatial dimensions, there's only one thing left, and that's into or out of the screen. And so the last one that I'm going to show you here is just that if I have an R like this, nope, that did not work. If I have an R like this, and I apply the force this way, right, we can see that this is doing the opposite of my red force and radius up here at the top. And so this one, and you can, once again, you can take your right hand and you can wrap it around in the direction that the wheel would be spinning based on this light blue force. And if you stick your thumb off to the side, it should be pointing towards you, so out of the screen. Oops. There we go. So if you had these forces at these radial distances away, all acting on this wheel, what we would end up having is, if we assume all the R's and F's are the same, is we would have this force and radius, plus this force and radius, plus this force and radius, plus this force and radius to get the total. But this one might be negative. We might define this as the negative direction, for instance. And so we'd end up with RF plus RF plus RF minus RF, giving us a total torque of 2RF. Okay, so that's how we add the vectors in a case like this. All right, hopefully that makes some sense. Now what we're going to do is we're going to take this a little bit further. So there's a term that we know in linear motion called mass. And mass is the thing that resists changes in linear motion. So forces cause changes in linear motion. Masses resist changes in linear motion. Likewise, there's a term, a similar term, an analogous term in angular motion called I. And this is called the moment of inertia. Okay, so I'm just going to write that down here. Moment of inertia. And it's an I, obviously, for inertia. So, what is the relationship between I and M? Because we've all had these conversions between these things. This is the most confusing thing, and it's really the most important thing in terms of a distinction between the linear and angular variables. Okay, so this is a sigma, and so what it's saying is that to get the moment of inertia of something, you add up all the masses and all of their perpendicular distances from the axis of rotation squared. We'll start with a very, very simple case. With this, just a ball on a string. So that'll be our center point, and this will be the ball on the string. And we'll give it a mass m, and it's a distance r away from the axis of rotation. Now we're assuming here that the string is very, very light, and that the mass is essentially a point mass. Okay, so that's the assumption that we'll make. Since we only have one, we only have one mass here. When we go ahead and we add up our masses times, so we have r perpendicular squared times m, because there's only one mass and it's all located at one position, we end up having mr squared. So this is our basic equation idea for a point mass at some distance from the axis of rotation. Okay, and just so that we get a sense of things to box here, I kind of omitted that. That's boxed and this is boxed. Okay, so this is for a point mass. Now I want you to imagine that we have, instead of just one point mass, we have 2 point masses. And it doesn't really matter where they're located, so I'm just going to put one over here, 2, and I'm going to call this one 1/2 of m. And I'm going to put another one off like this, and these are both a distance r away. So what I'm trying to say is that their orientation doesn't matter. The angle doesn't matter because the mass is, in each case, a perpendicular distance of r away from the axis of rotation. So if I apply my formula of r perpendicular squared times m, what we're going to end up getting in this case is we have our I equals 1/2 of mr squared plus 1/2 of mr squared, and we end up getting the exact same moment of inertia that we had before. Why is this? Because we have the same amount of mass located the same distance away. Alright, so I'm going to cut this video off because it's starting to get a little bit long, and we're going to pick up with moment of inertia in the next video. Hopefully I will be able to explain a little bit more about moment of inertia and the role that it plays, and talk about the moments of inertia of a variety of different things.